Hi, and welcome to my talk about pandas and accessing SQL databases using pandas read and QSQL. In this talk, I'm going to show why it is quite simple to access these, despite the complex things happening behind the scenes, why it isn't that fast at the moment, how you can get first the alternative, and how we at the end actually can get it fast by default. Before diving now into the actual talk, I want to give you some context about who I am and why do I concern with this. I'm a data engineer at the software data science project company QuantCo. We work with different clients that have different kinds of data. And this data is typically stored in a relational database management system. They're quite different, so we have seen quite some of these challenges. Besides my main work, or during my main work, I actually contribute to open source projects. Important for this talk, I'm a maintainer of Apache Arrow and Apache Parquet, and I'm also a maintainer of DBDBC. I do lots of other open source stuff, but this as a bit of disclaimer because I will use these technologies in the talk to make things faster and so you get a context why I may be choosing that. I have a bias because I'm the maintainer. Now, going back to our talk. The setting we have is that we like tabular data, meaning we have a lot of this data that has several columns, and each column has a name, and everything in the column is of the same type. And we're Python users, we like to do things in Python, so we use pandas. In this talk, we're actually talking about large amounts of data. Large amounts can start already with 10,000 rows, but can go up to 1 million. A lot of these things, performance-wise, the show don't make sense for us if you just get a single row result from your database or so. And on the other side, going out of our pandas bubble, Python bubble, the traditional storage system, where you actually would store tabular data, where people in the business modify it, is in a relational database or in a SQL database, using it the most common language to access that. And we're now concerned, how do we get from this traditional SQL database, or not always traditional, but traditionally there, into pandas? And once we have done things in pandas, how do we get it back in again? In pandas, there are two functions, which are also part of my slide or my talk title. The first one is pandas read SQL. You can use that to read data from an SQL database into a data frame. And there are two main arguments you need for that. The first is the SQL argument. It can be free, like the select star from table, or if you only want to select a full table, you can just supply a table name. You don't even need to write SQL. And the second argument can be an SQL Alchemy connectable. SQL Alchemy has several things you can use to connect to a database, or a string, which is passed to SQL Alchemy, or a SQLite free connection, which is a special case here if you're talking to a SQLite database. All other database types are supported with SQL Alchemy. And writing a data frame back into the database works with the toSQL function. As with the read SQL function, it has two main arguments. The first one is the name of the table. So here you can't be that flexible. You have to write to exactly one table. And the connection is the same connectable as you passed into read SQL. But it's pandas, so it has a huge set of flexibility, and the flexibility is exposed by having additional keyword arguments that you can use if needed, and don't have to use. But that's also the big power, that you can expand from a simple interface to much more complex things, which is adding the bits you need. The first thing is the if exists parameter. Typically, if you write toSQL, pandas also has the magic that it creates the table if it's not there, and takes care of setting the right data types, because you know the data types because they're using the data frame. Now, the thing is, it can create a table, but sometimes the table already exists, and then you need to tell pandas what it should do. The first case is the table exists, and you don't want it actually to change anything, because you have that one process that writes the data once, and once it's written, it shifts data and it shouldn't change. So in that case, if you want to tell pandas, please fail, please don't change my data, there's one golden copy and leave it as is. Sometimes, the latest version is the best version. In that case, you can tell Pandas, okay, if there's already some data inside, drop it and rewrite it with the latest, greatest things. Otherwise, if you have a workflow that's running on a daily basis and you have a table that spans all time, you just want to append the data you're just running. So you can Pandas, okay, if there's already a table, leave the table as it is and just add my data at the end. A big difference between Pandas and a database system is that Pandas has this column called index. In the database, you also have an index, but an index is not additional data. It's a data structure used in the background to give you faster access to specific rows. Database pre-computes some data structures that help it point faster to things, easier find out where something's lying on disk. In Pandas, an index is an additional column. It's a special magical column which gives names to rows. The simplest case is that you have a range index, meaning going from 0 to the number of rows you have, but it could also be something different, like actually string names for that row. And you have to tell Pandas what it should do with that when it's inserting the database, because the database has no notion of this index. The default behavior is that it will insert an additional column called index and store the index there. But you can change that. You can either set index equals false and just don't insert a database, or if you keep the default true, you can set a label and then insert the column to that label. When you're inserting data, especially if you're inserting large amounts of data, you can tell Pandas with the chunk size parameter to insert less of it at once. This either has the benefit of not overwhelming your database system or not overwhelming your Python process that inserts it. Because inserting in Pandas is not as efficient as it can be. That's why I'm making this talk. But one of the problems is that in the process of inserting into the database, we're creating a lot of temporary data structures in Python that take up memory. And if you do it chunk-wise, the memory peak will be lower. So if your machine is quite limited by memory, using smaller chunk size may cost you more time, but it also gives you the benefit that you need less RAM. But in some cases, that's quite a good trade-off. We have a data frame, and each column in a data frame has a data type. And we can use that to insert with that into the database. But sometimes you have different data types in your database because Pandas knows one datetime. It has the one datetime 64 of nanosecond precision. Actually, the database knows a lot more datetime types. Depending on which database you're using, there could be over 10 or 20 datetime types. And to actually tell Pandas what is the right one to use, you can supply it here, because guessing is not possible if you have 20 options. And the last one is the method parameter. Pandas does a lot of cool magic in the toSQL function, like looking, is the table already there? If not, infer the data type from the data frame, you select the correct matching data types in the database, and create a table and so on. But inserting to the database can be optimized. And Pandas provides a toSQL function already a hook called method, where you can supply callable that gets the name of a table, gets a connection, and it gets an iterator over the rows of the data frame. And you can insert with that into the database. You can use that to speed up things, especially for Postgres. But it sadly only gives you a data iterator over the data frame rows. It doesn't give you the exact data frame, making it not as good as it needs to be to do the optimizations we're doing later. So this is when we can hook in today, but it doesn't provide a perfect interface yet. Now, what I've skipped over a bit beforehand was SQL Alchemy. I told you there is a SQL Alchemy connectable, but SQL Alchemy is actually the main part doing the magic here. It's a Python toolkit that you can connect to very vast amount of databases supporting SQL. And it gives you a uniform interface for that. Meaning, if you want to get metadata of a table in your database, you can just use SQL Alchemy and get a meta object of the table, writing plain Python. And for every database that's out there and has a SQL Alchemy driver, someone's written the glue code that connects the SQL Alchemy API to this special SQL dialect for getting the metadata of the table. That's actually one where nearly every database is different from another database. But we have this one uniform API. And it also gives you the ability to connect to every database using one uniform interface. And there's also a thing called the object relational mapper. Object relational mapper gives you the thing that you can define a Python object with attributes and connect it to a database table. That gives you transparent, like if you save this object or make changes to that, you can see the change directly in the database. That's the thing we're not using here. But what we need in Pandas is the metadata layer so that we can find out about which tables are there, what is the schema name, and the engine interface, which allows us to connect to all these databases supporting SQL Alchemy using the same interface. And due to the magic, what is done in these SQL Alchemy drivers for the databases, Pandas doesn't actually know any specifics about a database besides for SQLite. And so every database that you want to use in Pandas only needs SQL Alchemy support, doesn't need anything specific for Pandas. That means that Pandas doesn't actually have so much SQL code for its support. That's a really nice thing. Because if you want to look what's inside working with Pandas, it's mainly delegating to SQL Alchemy. And to find it out, a good idea is to start a Postgres instance locally. You can do that by running a Docker container. That's a thing that works, like this command works on nearly every Linux system if Docker installed, and also works on a Mac. And we can then use SQL Alchemy to connect to that. That's an easy way how you get a locally set up database instance. There are various other ways, and if you do it in production also, there are much, much better ways than doing that. But just for getting it up and running for this talk, this is quite a nice thing. And once we have now set up a new, fresh database instance, there's no data inside. So we're going to insert some dummy data, but at least take care that we cover like the typical data types we're going to use. I'm skipping over datetimes here. They work too, but as I said before, there's so many types. We don't need to get into complexity in this simple example. To get that into the database, we can directly use the toSQL function. We push the data into the test table and use the connection we used from the Postgres database. I'm using here ifexec replace because this is my test code just to show you things. And I just always want the table to be exactly the data frame I have, but I want to be able to execute the code how often I like. So we're just going to replace what's there. To then see what's inside, we can use the plain SQL Alchemy interface. We can give it the select star from test table command in SQL, which will just fetch all data which is inside. That returns the SQL Alchemy result, and we can fetch that. And then we get the typical Python interface of the database result, which is a list of rows, and each row of the database table is presented as a tuple. That's, if you want to iterate over the tail, a nice data structure, but actually it's not the thing we need in Pandas. Because in Pandas, we not actually want to have a list of rows, we want to have a list of columns, we want to have names, we want to have every value of a column in a NumPy array with a fixed D type. So this looks okay. We know it's the data we inserted, but it's not a shape we want to have it. And therefore, we can use the Pandas read-SQL function. The read-SQL function can execute the same query, also use the engine, but it will return for us a data frame. And here you already see that we inserted the data with Pandas because we got 4 columns. And we have the special index column, which we didn't actually see in our data frame, but is there in every data frame because we create a data frame with default index, range index. But if we fetch it again, Pandas has no notion of knowing that the column that is called index actually the Pandas index it has inserted before, because it can't store this anywhere. So this information is lost. We can now do reset index and use the index column as an index. We can use it as it is here, or we can just drop it. But that's depending on how much of the use is the index for your database. And now the important bit is, how does it actually work inside? And read SQL, the first thing it does, it actually delegates everything it does to a class called SQL Database. SQL Database is the internal Pandas class, which does the talking to the SQL Alchemy interface. And reading data is actually not so much code. It would execute the SQL query you gave it with SQL Alchemy. SQL Alchemy result has a property called keys, which you can ask, and it will give you the names of the columns. And depending on whether you use the chunk size parameter or not, it will just call result.fetchAll and get a list of rows as we got in the previous example and fetch that into the local process. And Pandas has a custom constructor for a list of rows. This is the from records constructor, and we call it with the rows and the name of the columns. I said before, Pandas has a lot of magic in its keyword arguments, and here's also then a bit of this magic happens afterwards once it's landed in a data frame. Some databases return dates as strings. We can pass them here, and also we can tell Pandas will do the thing you told it to do with the index column. Set it, drop it, or do something else. Basically, we're delegating most of the complicated work, like speaking the different dialects to a database, to SQL Alchemy, and it's not done instead of Pandas. And the other way around, the SQL statement is simpler, but what we do is actually more tricky. Because we need to first check, is the target table already existing? If not, what is our strategy? What will we do? Typically, if not existing, we will call a create table. We tell SQL Alchemy the name of the table and the data types we want, and SQL Alchemy will then use its translation API to translate it to a SQL statement so that the database will create the table. And afterwards, we will insert that table into the database by using a list of tuples per row. And that's done by just converting the data frame back to this list of tuples. Because SQL Alchemy and the general Python DB API has no notion of Pandas data frame. So we're getting back to plain Python objects. And that's actually the main reason why it's slow. I'm going to show you some benchmarks later. But now I'm actually going to first give you the theory why it actually is slow. And it's also the same thing why Pandas is fast or why NumPy is fast. When you look at a structure of a Python list, it's really flexible, it's really easy to use. But the flexibility it gives you also comes with a cost. In Python, everything is an object. That means for accessing everything, when you look at an object, Python first has to look into this object. What kind of object is it? It needs to store for each object a header where it knows the type and what fields it has. And when we know the fields for a list, we know it has a certain length and it has a list of memory pointers to all of its items. So if we want to access an item, we go to the Python object, see it's a list. We look at its items, we see a memory pointer, and the memory pointer has the location of another Python object, which we then can access. But we also have a header and can look inside of it and see, oh, it's an integer. So I have 8 bytes of data, and I will read that and have then my integer data. For the next element in the list, we have to go back to the items list, because it has a different memory address, or maybe totally different location in memory. So we then go through the same thing, see the object is at that location, see it's an integer, so we read the next 8 bytes and have the integer value. An NumPy array has the simple constraint that it assumes that everything in this array is of the same data type. Meaning that if we have an integer array, we have one Python object with the header telling us it's an NumPy array. This is its size, and the data is located here. And if you look at the data, it's not a list of memory pointers pointing to where the data is, but it's actually directly the data. Meaning that if you want to get the first value, you go into data and just pick the first one. And that's 8 bytes of an integer, and the next one is the next 8 bytes. That means that you have less overhead in accessing these things. And it's not just the 2 jumps you got rid of, but you only have 1 memory jump from the object to the actual content. But it also means that if you want to read a second value, you just read the next 8 bytes. And luckily, if you access memory in your computer, if you read the first value, it will already fetch like 64 kilobytes or so out of memory into your CPU caches. And then you can read the next 64 bytes really fast. The next 128 bytes of that row will be semi-fast and so on. But it will be much, much faster than accessing just any other random object in memory. And as long as you keep your data in NumPy arrays, it's really efficient. You have the limitation that everything needs to be of the same size. It's not easily appendable like a Python list, but it's also a bit faster given you can live with these constraints. And that's also a big difference why Pandas read SQL isn't as fast as it could be. Because we're passing SQL query to SQL Alchemy. SQL Alchemy fetches Python objects for us. And then we take these Python objects to create a data frame. But if you have 1 million rows with 50 columns, we will create 50 million Python objects in SQL Alchemy, and we'll directly get rid of them again when we create a data frame because we don't need Python objects there. We use something much more efficient. To show you the overhead, I'm actually going to use Parquet files because this is like the most efficient way how you can store a data frame on this. Because in the database world, you have actually 2 components that make it pretty costly. It's the time it takes to execute on the database and the time it takes you to fetch the result into a Pandas data frame. I'm only talking here in this talk about how long it takes to fetch the result. But as these 2 components are involved, we're going to skip the part where we talk about the time it takes to fetch it from the database, or the time it takes to compute a query. And reading that in a Parquet file, we can either select to read it directly into Parquet, which takes 2 to 3 seconds, or we can use the PyArrow interface, read it into an arrow table, convert it into a Python dictionary, which is like the huge amount of Python objects, and then convert it directly back to a data frame. In both cases, we get the exact same data frame, but in one, we don't construct any intermediate Python objects, and the second one, we construct like millions of intermediate Python objects. And we see the difference that the second one takes up to 3 minutes, the first one takes 3 seconds. Which makes a really huge difference if you have the same difference in accessing the database. And this slightly takes us to the point, how do we get it fast? And the obvious thing is here, we want to get rid of these intermediate Python objects. We either want to fetch directly into the data frame or some efficient structure which can be converted easily to a data frame, which doesn't cost us so much in conversion. For that, one of the typical standard APIs people use to access a database is ODBC. It's a standard API set in C++, how you can access the database, given some APIs. This is like the SQL Alchemy metadata interface of the native world. There are 2 popular libraries for that. The most well-known is PyODBC. It's the most mature. A former colleague of mine has written TrueODBC, which does the same things as PyODBC, but with some performance optimizations inside. So it's like 20% faster. We're actually interested in the arrow support of TrueODBC because that's a thing where it has a different API than PyODBC, because PyODBC and TrueODBC both implement the PEP 249 DB API 2, which gives you a list of rows in Python. But TrueODBC also supports fetching into an arrow table. Arrow is an open source project which defines a uniform memory format for columnar data in a lot of languages. There are over 10 supported languages currently. And data format looks quite similar to a data frame. And for us, importantly, you can access error tables from C++ and from Python. And in TurboDBC, we have support for fetching data from ODBC into Arrow memory and then passing just a pointer to the error table to Python. And Arrow has support for really, really fast conversion from Arrow to Pandas, which gives us a bit of overhead, but it's like 100 times smaller than the overhead it would take to convert from Python objects to Pandas. And this is one of the tricks we can use to get faster access to databases that have a decent ODBC driver. Databases with a decent ODBC driver are MS SQL and Exasol. Here in both cases, there's a talk of Michael König, the original author, who shows that you can get a 3 to 4 times speed up using this Arrow interface in TurboDBC compared to using the SQL Alchemy interface Pandas Read SQL is using. There are other databases like Postgres. They have an ODBC interface that's working, but actually not so good for big result sets. That's a case where you could use that approach. You maybe get like a 10% increase in performance over the SQL Alchemy interface, but in some cases you don't even get one because the driver in ODBC itself isn't that performant. That's where you need to do different approaches. TurboDBC is nice because it can retrofit this performance to existing drivers, but you still have the conversion in your driver. You're fetching it in ODBC, you convert it to Arrow, and you convert it to Pandas. That means there's still some overhead. Snowflake actually is one of the nice modern databases that comes with a simple JSON interface that is readable in every language without dependencies. But it also has the support that actually the database server itself can give you the results set as Arrow. Meaning the client fetches the Arrow data structure and doesn't need to convert its results also into Arrow before converting it to Pandas, but directly fetches in Arrow and only does need to do the Arrow to Pandas conversion. And the Arrow to Pandas conversion is really, really fast. So that fetching result from the database isn't actually taking that much effort. On the website, they have a benchmark where they improved the drivers using Arrow. They did some benchmarks about how the drivers in the backend with a stable API got faster, and then how much faster they got conversion to Pandas when they didn't use the standard Python API, but passed the Arrow results directly to Pandas. And they see a speed up of times 10. And I'm actually also using that driver, and the times 10 speed up is actually what I'm also seeing in production. So this is really nice. And this is what you get if you get rid of all these transformations in between and have like a tiny Arrow to Pandas conversion, which is even in some cases zero copy. These are two typical cases how you generally can make it faster. JDBC is the Java world equivalent of ODBC. I've written a blog post about that. It's here on the slide so that you know how it works. It's quite complicated. So I'm not going to go into detail here. The important thing is you can use that to fetch things on the Java side. You get Arrow back, and then you get a reference to the JVM memory and can convert it directly to Pandas. It takes an awful amount of time to set this up because it depends on how your drivers are stored. You need to get a JARS at the right place. But if you're using a database that only has decent JDBC drivers and nothing else, actually it's worth going that effort, because in my simple benchmarks, I already had over 100 times speed up. So spending 4 hours and getting that set up, it may well be worth the effort. It will be complicated, but it could pay off you quite a bit. As I said before, Postgres doesn't have a good ODBC driver. Postgres has a copy interface, which can give you the result as a CSV or as Postgres binary format. You can use that. This is for the CSV output. There's even an example in the Pandas documentation to use the binary format. You can get a bit of more performance. I may open source something in future. It's a bit more tricky, but it also gives you a bit more performance. That was now an example how you can get it fast with 4 different interfaces. We would like to have this actually as part of Pandas Read SQL. Mainly because if you look at it, Pandas Read SQL is a simple API, 2 parameters, and you create an engine with SQL Alchemy. To be DBC, you need a connection, you need a cursor, and then you need to call fetch or error to Pandas. Also not that complicated. The thing is coming in, when you look at Snowflake, it's doing nearly the same thing, but it's not exactly the same thing. So for Snowflake, you need to have a similar but different approach. For JDBC, it's much more complicated. This is the most simple form you can get it, and it's quite dense to what we're doing here. Postgres is even more complicated. So the thing is, you need for every database, you need a custom solution, how to connect to it, and you need to know what actually the parameters are. And if you want to support more than one database in your code, you need a lot of ifs. So the nice thing would be get a performance we get with using these custom interfaces, but have it in Pandas. And for that, we actually want to have something in Pandas. One thing we could use here is that actually you can ask SQL Alchemy for the underlying connection. Like in my case, if I call on a Postgres connection, I go to the raw connection, I get a CyclePG class back. And then I can maybe do something special on that in Pandas. Because I don't actually want that my users learn a new API. I just want them install this package, maybe use this keyword, and you get performance. But a single keyword would be nice, like calling it engine equals to VDC. And then still use Python or Pandas to read SQL. Another approach would be that Pandas defines a database engine class and says, here are 3 different methods. Here's give a data frame and a table name inserted, and the other way around, please read it. But Pandas is only giving you the insertion. Setting up table names, data types, and so on. Pandas can handle for you that. That's done in SQL Alchemy. And performance there is no issue because creating a table is not dependent on the size of your data, but it's the same performance if you insert one row or if you insert multiple rows. And I can write this one implementation, give it a name, and I can call it Pandas Read SQL. And in this case, engine equals fast engine, and it just works. Discussions for that on the Pandas issue tracker. If you have better ideas, please weigh in. I'm maybe going to do an implementation of that, but getting into some support will make it faster. That was all my talk. I hope you got a grip that Pandas and SQL databases actually work quite well together. If performance of larger results is an issue for you, I've shown you some ways how to invest some time but get it faster nowadays. And hopefully you're all looking forward for the future where it's not so complicated anymore, but can just select an engine in Pandas and get the performance you get with more complicated queries. Thanks for watching. And for everyone who's at the conference and the Q&A session, now is your time where you can ask questions. Otherwise, ask them on Twitter and I will try to answer them.